Welcome back to the next video, everybody. Today we are going to conclude the proof of Fermat's last theorem for exponent 3. Please watch the previous video in the Fermat's last theorem playlist, Fermat's last theorem for exponent 3 part 1, if you have not done so already. So if you watched the last video, here's what we're trying to prove. Fermat's last theorem, let n at least 3 be an integer, then x to the n plus y to the n equals z to the n, where x, y, z isn't 0, has no solutions over the integers. We proved in the first video in this playlist the theorem in the case n equals 4. And we also, last video, proved the theorem in the case n equals 3, assuming that the following is true. We'll call this Eulers Gap. It says the following. If k and l are integers, and they're coprime, and k squared plus 3l squared is a cube, then there have to exist integers alpha and beta, such that k is alpha cubed minus 9 alpha beta squared, and L is 3 alpha squared beta minus 3 beta cubed. So we proved Fermat's last theorem in the case the exponent is 3, assuming this is true. Okay, so we're going to prove this in this video. So let's reduce the problem. Let's notice the following. You can write k squared plus 3l squared as k plus l times root negative 3 times k minus l times root negative 3. If one of these two factors here, let's say k plus l root negative 3, is a cube of the form k plus l times root negative 3 equals alpha plus beta times root negative 3 cubed for alpha and beta integers, then it's very easy to check, and I advise that you do so, that k minus l root negative 3 is alpha minus beta root negative 3 cubed. This is one of several things I'm going to ask you to check as just a little bit of homework, or else this video will take way too long. Okay, and so the equation k squared plus 3l squared equals k plus l root negative 3 times k minus l root negative 3 turns into the following. If you plug these expressions in, you get alpha plus beta times root negative 3 times alpha minus beta times root negative 3 all cubed is alpha squared plus 3 beta squared all cubed, and all of that equals k squared plus 3l squared. So what am I trying to say here? What I'm trying to say is that to find a cube of this form, k squared plus 3l squared, you really just have to solve this equation here, or well, one of these two equations over z. For example, you just need to solve k plus l root negative 3 equals alpha plus beta root negative 3 cubed for alpha and beta over z. Because once you've done that, you'll be able to write k squared plus 3l squared as a cube. Okay, so now this is the wrong direction, right? What we need to prove is the converse. What we need to prove is the following. So Eulers Gap rephrased. Suppose k and l are coprime integers such that k squared plus 3l squared is a cube. So now I'm not trying to find a cube as per the previous discussion. Now I start with a cube of this form. Then there exists alpha, beta, and z such that k plus l root negative 3 is alpha plus beta times root negative 3 all cubed. So this is the converse of the above discussion. Again, if I can prove this, I claim that Eulers Gap, as originally stated on the second slide, is also proven. So why is that? So why will we be done if we can prove this rephrased version of the gap? Well, by the binomial theorem, or just by direct calculation, if you can solve this equation, so if you can solve k plus l root negative 3 equals alpha plus beta root negative 3 cubed, well, what is alpha plus beta root negative 3 cubed? Just use the binomial theorem, and you get that that's equal to alpha cubed plus 3 alpha squared beta times root negative 3. Plus 3 alpha beta squared times negative 3, plus beta cubed times negative 3 times root negative 3. And after you simplify this and match up coefficients, you see immediately that k is alpha cubed minus 9 alpha beta squared, and L equals 3 alpha squared beta minus 3 beta cubed, which proves the Eulers Gap as originally stated on slide 2. Okay, so I've reduced the problem down. Now, to finish the proof, I just have to prove this. Okay, so k squared plus 3l squared is cubed, k and l are coprime. I can find integers alpha and beta such that this equation here holds. I have to prove that, and then I'm completely done. So let's do that. The proof of this is somewhat difficult. We'll do it using a succession of 4 lemmas. Lemma 1, suppose k and l are coprime integers, and that k squared plus 3l squared is even. Then k plus l root negative 3 can be written in the form 1 plus or minus root negative 3 times u plus v root negative 3 for an appropriately chosen sign and for some coprime integers u and v. Okay, let's prove this. Since k squared plus 3l squared is even, it must be true that k and l have the same parity, so check that. But k and l are coprime, so k and l have to be odd. Well, that means each of k and l must be of the form 4n plus 1 for some integer n and z. Of course, n might be different for each of k and l, but the point is you can write k and l in this form. The upshot is at least one of k plus or minus l is divisible by 4. So check that. Okay, let's say it's k plus l that's divisible by 4. Then when I write 4 times k squared plus 3l squared, which is incidentally 1 squared plus 3 times 1 squared times k squared plus 3l squared, I can use my identity from the previous video, which tells me how to multiply expressions that are both of the same form, something squared plus 3 times something squared. I had an identity last video that tells me how to easily multiply these and get an interesting, useful expression out of it. And that expression gives you k minus 3l squared plus 3 times k plus l squared. If you don't like what I just said, and or you didn't watch the last video, A, go watch the last video. But B, you can just check these are equal, right? Okay, so if I divide both sides by 4 squared, what do I get? I get k squared plus 3l squared over 4 is u squared plus 3b squared, where u is k minus 3l over 4 and b is k plus l over 4. Okay, this is a system of 3 equations that I'd like to essentially solve for u, right? Well, you can solve these equations for k and l in terms of u and v, because you can check easily, and I'll have you do that, that solving this is equivalent to solving u plus v root negative 3 is k plus l root negative 3 times 1 plus root negative 3 over 4. It's not a hard exercise, okay? And that's equivalent to solving, which I'll again have you check, the system k plus, or the equation k plus l root negative 3 equals 1 minus root negative 3 times u plus v root negative 3. But isn't that just what we wanted? I mean, okay, so we've solved this, hence we've solved this, but this is the lemma. The lemma is that we can do this, right? The only thing is we didn't take care of the case k minus l is divisible by 4, but it can be done extremely similarly, and I'll leave that to you. The other thing we didn't check is that u and v are coprime. But u and v are coprime because k and l are coprime. So for example, if you look at the lemma here, if u and v weren't coprime, there would be a common factor of u and v, but that common factor would divide k and l because of this equation here, you see, but k and l are coprime. So u and v are coprime automatically because k and l are coprime. Okay, lemma 1 done. Lemma 2, basically, what if now k squared plus 3l squared is divisible by an odd prime p? So suppose k and l are coprime integers, and suppose k squared plus 3l squared is divisible by an odd prime p. Then p can be written in this same form. It can be written in the form m squared plus 3n squared, where m and n are natural numbers and coprime. In other words, odd factors of k squared plus 3l squared, where k and l are coprime, are also of the form something squared plus 3 times something squared, where the two somethings are coprime. Okay? And furthermore, there's a second statement, k plus l times root negative 3 this time can be written in the following form, m plus or minus n root negative 3, where m and n are the squares, the things whose squares show up in the expression for p, times u plus v root negative 3. So almost the same as the last lemma, except for that we're a little bit more generic here. Okay? Again, for some appropriately chosen sign, and again, u and v are coprime integers. Okay, the first statement I won't prove. It's a well-known exercise in a number theory class that odd factors of numbers of this form are also of this form. I'll give you a reference, though. You can go look at Edwards' book, Fermat's Theorem, A Genetic Introduction to Algebraic Number Theory, Chapter 2, specifically Section 2.4, specifically bullet point 5 prime. This is one of Eulers' elementary results on sums of squares. Okay, it's a little bit tedious, so I won't prove it here. Okay, the second statement, though, is the one I'm kind of primarily interested in. That's this. So how do I prove this? It's very similar to the first lemma. As an exercise, check that either mk plus nl or mk minus l is divisible by p. I'll give you a hint. Take the product and add and subtract 3n squared l squared, and use what you already know in Euclid's lemma to see that one of these is divisible by p. Okay, let's say it's mk plus nl that's divisible by p. Well, when I take p times k squared plus 3l squared, which is m squared plus 3n squared times k squared plus 3l squared, and I use that same formula I used in lemma 1 from last video to multiply these out into a useful alternative form, I get mk minus 3nl squared plus 3 times ml plus kn squared. Or just check these are equal. Okay? If you divide both sides by p squared, kind of like how we divided both sides by 4 squared last lemma, you see that you can write k squared plus 3l squared over p in the form u squared plus 3b squared, where u is mk minus 3nl over p, and v is ml plus kn over p. In other words, similar to the proof of the last lemma, we have u plus v root negative 3 is m plus n root negative 3 times k plus l root negative 3 over p. So check this. It's an easy check. Okay? If you multiply both sides by m minus n root negative 3, you get the following. K plus l root negative 3 is m minus n root negative 3 times u plus v root negative 3. That's a quick little exercise for you to check. There's nothing to check. It's just a calculation. Okay? And so we're done. This is what we were trying to prove. The case mk minus nl is divisible by p is similar. It gives you k plus l root negative 3 is m plus n root negative 3 times u plus v root negative 3. The only thing we have to check now is that u and v are coprime, but again, it's u and v are coprime because k and l are coprime for the same reason as in lemma 1. Okay, so you have this statement here. If u and v have a common divisor, then so do k and l. Okay, great. Lemma 3. Suppose k and l are coprime integers. Then k plus l times root negative 3 can be written in the form plus or minus a bunch of factors that all look like, p sub I plus or minus q sub I times root negative 3, where p sub I and q sub I are natural numbers, and p sub I squared plus 3q sub I squared is either 4 or an odd prime for all I. Okay, so how do we prove this? It boils down to lemma 1 and lemma 2. If k squared plus 3l squared is even, it's divisible by 4. So check that as a hint. Just look at the equation mod 4. In general, since k squared plus 3l squared definitely isn't 1, and it's also definitely not 2, okay, it has a factor p, let's say, that's either 4 or an odd prime. So this is just a generic fact about integers. Okay, we've already used this, in fact, in my first video. Okay, if you use lemmas 1 and 2 in tandem, depending on the situation, you get, as a result, the following. You get that k plus l root negative 3 is m plus or minus n root negative 3 times u plus v root negative 3, where m squared plus 3n squared is the factor p that you're looking at. Okay, so check that. Check that lemmas 1 and 2 give this. It's not hard. We also saw u and v were coprime, and so you can iterate this procedure. You can repeat the process by, instead of looking at k plus l root negative 3, looking at u plus v root negative 3. You need the coprimeness of these integers to iterate the procedure, but you have it already. Okay, but factoring an expression of the form, let's say m prime plus or minus n prime root 3 out of this guy is the same thing as just factoring it out of k plus l root negative 3, except for that now u squared plus 3v squared is k squared plus 3l squared divided by p. And so this squared plus 3 times this squared is strictly smaller than this squared plus 3 times this squared. And so what I'm saying is, if you iterate this procedure, it terminates after finitely many steps. And what you get is k plus l root negative 3 is a product of a bunch of guys that look like, pi plus or minus qi root negative 3, one for each step of the iteration, times, times u plus v root negative 3. But after the last step, u squared plus 3v squared should be 1, because in all of the previous steps, we were assuming it wasn't 1, okay? So make sure you understand why this is 1. Just go check the second sentence of the proof and look what we've done so far. Okay, but if u squared plus 3v squared is 1, u is plus or minus 1, and v is 0. And so that gives us lemma 3. This is plus or minus 1. That's the lemma. Okay, so lemma 3 is done. Lemma 4. Let k and l be coprime integers. Then the factors in lemma 3, so these factors here, are determined completely up to choice of signs in the middle by the fact that p1 squared plus 3q1 squared times p2 squared plus 3q2 squared and so on up to pn squared plus 3qn squared is a factorization of k squared plus 3l squared into odd primes and 4s. Moreover, if a factor p plus q root negative 3 with q non-zero appears in the lemma 3 factorization, then p minus q root negative 3 cannot possibly appear in that factorization, and vice versa. Okay, this is not hard actually at all. What is the first statement really claiming? It's just claiming that the equation big P equals p squared plus 3q squared determines p and q up to sign if p is 4 or an odd prime. Well, if p is 4, this is completely trivial. Okay, so check that. If p is an odd prime, and if a squared plus 3b squared is some other representation of big P, then by lemma 2, and I want you to check that this does follow from lemma 2, A plus B root negative 3, so the kind of root negative 3 term stemming from the second representation, is equal to P plus or minus Q root negative 3, the factor stemming from the first representation, times some U plus V root negative 3 for some co-prime integers U and V. Well, I mean, what does this tell us? So remember, A squared plus 3B squared and P squared plus 3Q squared are representations of P. So this equation immediately implies that P is just P times U squared plus 3V squared. But that means U squared plus 3V squared is 1. And so U is plus or minus 1 and B is 0. And so A plus B root 3 is just plus or minus P plus or minus Q root negative 3, which is what we are claiming, right? We are claiming that this representation determines P and Q up to sign. Well, that's what this says, right? Okay, what was the second statement? The second statement is that basically P plus Q root negative 3 and P minus Q root negative 3 can't both appear in the factorization in lemma 3, but that's trivial because if they did, then when you multiplied them, you would have a factor of P squared plus 3Q squared in the factorization of K plus L root negative 3. But that's impossible because K and L are co-prime. This number would have to divide both K and L, and it's bigger than 1 for sure, right? Okay, let's prove the gap using the 4 lemmas. I can do it in one slide. Okay, let's take K squared plus 3L squared, and let's factor it into P1 through Pn. It's a factorization into 4s and odd primes, as in lemma 4. Now, K squared plus 3L squared in the gap is assumed to be a cube, and so 3 definitely divides n. More precisely, the powers of each distinct PI in this factorization are multiples of 3. There's a little bit something to check there for the 4s because 4 isn't a prime, but there's nothing much to it. Just write 4 as 2 squared and check it, okay? So in the factorization of K plus L root negative 3 given in lemma 3, the factors that you have corresponding to each group of 3 identical P's here, because there are groups of 3 identical P's here, 3 at a time, okay, the factors there must be identical because those factors, remember, are up to choice of sign expressions of the form P plus or minus Q root negative 3, where P and Q determine P. And the point is both signs can't occur by lemma 4. In fact, all this entire part of the sentence here is by lemma 4. Okay, so great. So here's what I can do then. All the factors are the same for each of the 3 identical P's, right? So what I can do is I can take one of those factors corresponding to each group of 3 identical P's, and I can multiply them all together. Take one factor per group of 3 identical P's. If you multiply them all together, what do you get? You get a number of the form C plus D root negative 3, because you're taking a finite product of expressions of this form ultimately. And what's true is that K plus L root negative 3 is plus or minus this number cubed, because you took one factor per group of 3 identical P's in this factorization. Well, you only took one factor per group of 3 P's, and all of the factors are the same for each P in a group of 3. Well, they're all the same for each P in a group of 3. So K plus L root negative 3 is this number cubed, okay? Up to sign, all right? So why up to sign? Well, in lemma 3, there was, let's see, where is it? Yeah, in lemma 3, there was a plus or minus out front. Okay, so you didn't get rid of that. Perfect. Well, we're just done now, right? Because I'm trying to write K plus L root negative 3 as alpha plus beta root negative 3 cubed. But the point is, if this is a minus sign out front here, you can just move it inside the cube, right? If it's a plus, you're just done. If it's a minus, just move it inside the cube, right? Negative quantity C plus D root negative 3 cubed is negative C minus D root negative 3 cubed, and you're done. Okay, so Euler's gap has been filled in modulo about a half a dozen exercises for you, and also just a tiny little bit of reading about Euler's results on sums of squares. It's very easy to read that. It's like a page in Edwards total to read all of them. Okay, so let me end the video by giving you some references. For background, for more information about Fermat's last theorem and its history, for much more on proofs of specific exponents, Niven, Zuckerman, Introduction to the Theory of Numbers. You've got Dixon, History of the Theory of Numbers, Volume 1 and 2. You have Hardy and Wright, an Introduction to the Theory of Numbers. You have Edwards, Fermat's last theorem, a genetic introduction to algebraic number theory. You have Cato, Number Theory 1, Fermat's Dream, although there's 3 books in that series, I believe. You have Ribbenboim, I think that's how you say it, Fermat's last theorem for amateurs, and also 13 lectures on Fermat's last theorem. You have Mordell's 3 lectures on Fermat's last theorem. You have Cox, Introduction to Fermat's last theorem, and so many more. I didn't list any of the more advanced references here that go through the general proof. I'm trying to give you references that go through things about specific exponents, background, number theoretic background, history, things like that. Okay, so what's left? If you do a little rearranging and you watch my first video, you see that it now suffices to prove the following if we want to prove Fermat's last theorem in general. Let P be a prime that's at least 5. If a to the p plus b to the p plus c to the p is 0, where a, b, and c are integers, then at least one of a, b, or c must be 0. So we will start looking at the general proof next time. So thanks for watching, and I'll see you then.